now it's a time to move ahead with the hands-on session, and our team member Evan Fernandez is here. And the most important part about this session is all the case studies which will be which our team members will be demonstrating in this during this workshop are done by students like you all. Okay, so students who volunteer by themselves, they can actually complete and submit a case study. They can also enroll themselves in our internship and fellowship programs. Definitely, we have a screening task and we have a selection process. But the students who join in our programs, these case studies are submitted by them. It is not that our FOSSEE team members have completed them. So it's a very unique part of the FOSSEE project that we train the learners and enable them so that they are capable of producing an output by the knowledge that they have acquired. Okay, so over to you, Evan. You can start the hands-on session.
Yes, ma'am. Thank you, ma'am. So welcome to the Industry Readiness Workshop, CFD Open Forum. Before we begin with the hands-on session, I would like to give a brief overview of how Open Forum case setup is set up. So most of you are beginners. For those of you who know already, it is really irrelevant. But for people who are really starting off with Open Forum, this is a good experience to understand how you set up a case in Open Forum. I'll be very brief with it. So this is your ideal case structure that you would have in Open Forum. You have three main folders. Okay, so you will have a zero, constant, and system folder. Now your zero folder, this is where you will be setting all your initial boundary conditions. So this can be your velocity, pressure, temperature, and in our case, we have some additional parameters as well for the demonstration. And next we have our constant folder. This is where you would save all the parameters that remain constant. Like if you are running an incompressible solver, then you would have your density remaining constant. You would specify your velocity, not velocity, but the fluid properties that you are giving. And some of you had asked Mr. Advait about where do you type in your properties and how are you getting your physical properties of your alloys and the material that you're using. So this is where you would be specifying all your properties within constant folder. And lastly, you have your system folder. This is where you would have your meshing parameters. You would have your control parameters, that is your start time, end time, your delta T, that is your time step. And you would have your schemes and solutions. So those are your discretization schemes, and any parameters like relaxation parameters and all that you require to tweak, those are where you will be changing your things. Okay. So the very first thing, so for a case, we will be downloading a case study that has already been published on our website. So if you go to completed case studies. Within that, you have a case study known as calculation of reaction-based residence time. Okay. It is done by an intern from a summer fellowship. So you can download this case. I already have it downloaded. So I'll show you why. Okay. So what this case is exactly doing is we have a pipe and we are going to be modifying a solver, that is your scalar transport form, to better understand or to simulate how a scalar moves in your domain. Okay. So by scalar, what we mean is like a scalar as a whole is a quantity that is transported in your domain without disturbing the flow. Okay. So you can think of it as like if you have a flow and in that you're introducing ink, like an ink jet. So that ink jet is not going to be manipulating or disturbing the flow that you've already set. So you're first initializing your flow and then you're introducing an external parameter and you just want to see how that external parameter is going to be transported in your domain from point A to point B. So for this very reason, you would have to first solve the continuity of flow equation, that is your Navier-Stokes equations. So for that, you would have your continuity equation and your momentum equation. So these are the equations that we have. Additionally, since we are using the scalar transport form, that particular solver solves your energy equation. So you would have your solver solving the energy equation as well. Now in our particular demonstration, we are solving for the flow as well as the energy equation. And then we're taking those values or the end product of what we're getting from the simulations and we're transferring that into a new solver that is custom made to find out the scalar transport or the scalar properties that we will be introducing separately. So in this energy equation, we have alpha on the right hand side, alpha and all the parameters. So your alpha is your thermal diffusivity, and you have K and then rho Cp. A is your thermal conductivity and Cp is your specific heat at constant pressure. So all these parameters will be essential when you are creating a solver. Okay. So keep in mind all these equations that you have, because if you want to develop a solver, you need to know the underlying physics that is going on. Only then can you better understand how and where to make the changes. So once we are done with the energy equation, this is the scalar equation that we have that we will be introducing in the new solver. Don't worry, I will show it step by step how is this process done. So you don't need to get overwhelmed by just seeing the equations. So for the scalar equation, we have our main scalar equation that is on the top over here. Now on the right hand side, we have the diffusion term and the reaction term. So for our case, we are keeping diffusion as 0 to simplify the whole equation. In your case, if you want, later on, you can tweak the parameters, you can increase diffusion and see how it affects your whole simulation. But for our case, we're just going to keep it simple. We have 1 hour, so we just try to push everything within that. So we have diffusion, which is set to 0. So obviously this term is going to become 0. And for our reaction term, we have basically changed the equation. So based on your reaction, it is a irreversible reaction. So you have like your reaction going from A to B, where A is your reactant and B is your product. So in that sense, we have the term on the right-hand side, ASC. Now this particular term, we are going to be solving using RNA's equation. So again, this equation will be put in your C file or your solver modified set files. So in this, A is your pre-exponential factor, E is your activation energy, T is your local temperature, and R is your universal gas function. Now in this entire equation, you have most of the parameters that are set to constant, only T being your variable parameter. So your local temperature is what you will be getting from your flow equations, okay? That is the reason we are solving for the velocity, pressure, and temperature. So we are first going to solve those equations, then come back to these equations and input those values within this. So these were the equations. Now coming to the solver itself, okay? So let's first start with the case. So suppose you download the case, you have, this will be your case. Once you extract everything, you will have these files. So you can open the case files. Now within this, you have the report. You can open the report and you can read this because all of the equations and where the changes are made are specified within this report. It's well detailed, so it's good. You can read this and can go through this. So once you open your folder, you must first go to the solver setup. There is a README file as well. You can open this as well. So let's open this. So in your README file, these are the basic instructions of how to compile the solver, how to run the solver, and any changes that are required. All of these are mentioned in the README files as well. So it's always beneficial to first read all of these files and then start doing something. Otherwise, you might end up doing something and you don't know what is wrong exactly in the whole setup. So once you read the README file, you can open the solver setup. So in the solver setup, you have this new scalar transport form. Okay. So you can open this and you have a create fields modified and you have the new scalar transport form. That is your basic C file. Okay. And along with that, you have a make folder. Within make, you have files and options. Okay. So I've opened these files. So on the right hand side, we have our original files, your scalar transport form.c file. And on the left hand side, we have the modified files. Okay. Now, where can you find these original files? Because you have to obviously copy some of these and then modify them to make your own solver. So in your file structure, when you go, so suppose I open Ubuntu. Okay. So once you've entered your Linux environment, it's at the bottom here. So you'll have Ubuntu 2204. Now, since we're using OpenFOAM 9, your folders are always saved in your OPT and under OpenFOAM 9. Okay. Under OpenFOAM 9, usually we go to tutorials to copy some tutorials. But in this case, we want to go to applications. Within applications, we have solvers. And now over here, under basic solvers, we have scalar transport form. So you can see over here, we have the scalar transport form C file. Then we have the create fields, that's a header file. And then you have again, these additional make files, in which you have the files and options. These are where you will specify your libraries and where you want to save your solver and all those parts. So once you open this file, we first go with what is in the make folder. So in your make folder, you would have options and you would have files. Same goes for this one. Okay, options and files. Now, the very first thing you will notice is whenever you are modifying a solver, the very first thing you do is always change this path, that is form user app bin. So originally you will have it as form app bin. You should always change it to user app bin. What this does is that in case you're making a new solver, like if I were making scalar transport form and say I save it as scalar transport form, how will OpenFOAM or the whole Linux environment differentiate between which scalar transport form you're trying to enable? So for this very reason, we make a user-defined app bin. So what this does is it will store all your custom solvers within this user bin. Okay. So if you create something that is wrong or you cannot change it back, it is at least saved in a user bin and it is not affecting your original files that you have for OpenFOAM. So that's why first thing you do is change the username. Basically, you change this path and you put user before app bin, and then you can add your custom name. So now in this case, he thought of writing new scalar transport form modified solver. Okay. So in this case, we have the scalar transport form. Once you're done with the files, you can save this. Then you move to the options folder. Okay. Now in the options folder, most of the times there isn't much of a difference because you're using the same libraries, provided you are trying to modify something on that base level. Now, if you're modifying something to an extreme level, you would change some of the libraries because you would have to introduce some libraries and anything that you are trying to introduce in your solver itself. So these are some of the things. Now, if you're changing versions, usually whenever you're changing from say OpenFOAM 9 to OpenFOAM 12 or something, some of these paths are a bit different. So again, depending on the version you are on, just check these paths, because sometimes in the newer version, they have tried to summarize everything within one folder, whereas in the older version, it was segregated into multiple folders. So you can always check these. But ideally, you would have no problem running this on OpenFOAM 9. Okay. And the user even mentions that these particular files are created specifically for OpenFOAM 9. So if you are trying to run it on another version, you would have to check the compatibility. Okay. So once you have made some changes in your options folder, you can go to the .c file. Okay. So now in your .c file, on the right hand side, we have the clean one, and on the left hand side, we have the modified one. So the very first thing you would do is you have this particular block, okay? Include block. So this is where you are calling all the header files that you have. Like if you know basic C++ coding, C++ coding, you would have to call some headers if you don't want to cluster up the whole C code. So you would have a header file and you would have the .c file. So in your header files, it's usually where you specify any of the important parameters you want. And then in your .c file, you just call those header files. So that is what is happening over here. We have the CFD header files, FE models, FE constraints, simple control. So all of these are the header files, but in our modified case, we've just mentioned an additional file called as dimensioned constraints fold header file. What this does is it will just give us can say liberty to modify some things in your constant folders or in any of the constant parameters. Additionally, if you scroll down, you have again some more header files. And over here, we have something as the create fields header file. Okay. Now, if you noticed over here, we have that create fields. This is where you would specify all the parameters that will go in yours. Like if you want, you can add your transport parameters. Like in our case, in the PPT, if you remember, we want to introduce these additional parameters as a constant. Okay. So in the transport properties, we will have to introduce these parameters. So those are where you will be mentioning over in your create fields, you will be mentioning all these parameters. Okay. So before we go more deep into the C file, let's first see the header files. Okay. So in our header file, in the original case, we have a header file for temperature and we have for velocity, okay, because it's solving these two equations. But in our case, we want to introduce a scalar. Okay. So this scalar, we'll be naming it as scalar 1 and a scalar 2. So we have two scalars. And additionally, you can add some more scalars, like if you have 4 or 5, just as Mr. Advait said, in case you have multiple, like he has been solving for 4-phase. So anytime you want to introduce any new parameter or any new material, you can do that within this create fields modified H within your create fields header file. Okay. And then you have to specify the same in your .c file. So these are just the header files. You have to mention that in your C file for it to properly function. So first we are mentioning a scalar 1 and scalar 2. Okay. We are specifying some basic parameters that it should be like runtime, it should run with the whole simulation and all those stuff. Must read, auto write and all that. So those are the basic parameters. As we move forward, you have the U, that is your velocity. So that is the same as the one that is in the original file. And we also have T, but since we are solving for Arrhenius equation, we have clubbed that all together. So you'll see that in a minute. Then once you are done with specifying, now all these files that are before transport, these are which will go in your 0 folder, okay, your initial boundary condition. So if you were to open a scalar transport file, so in the file that we have, the demonstration file, we have the solver setup, and also we have some laminar case. Okay. So I'll show you the flow file. In this, we have used for temperature a scalar transport form. So if you opened this, you would have primarily in a scalar transport form folder, you would have T and U. Okay. Because we're solving for only these two equations, whereas in a flow case, at least for simple form, you would only have velocity and pressure. Simple form algorithm does not solve for temperature. So those parameters you have to introduce in your new solver. Okay. So this is where you're doing this. You're introducing some parameters. So the next time you compile this solver, you will, if you don't specify any of these parameters like scalar 1, scalar 2, in your 0 folder, it will prompt an error and saying that these files are not introduced or are not mentioned in your 0 folder. Okay. So once your 0 folder is set up, all your parameters that you want to set within that is set up, we move to the transport properties. Now here is where we are going to be introducing all those parameters like Arrhenius equation, any of the equation that we're using in the energy equation. As I said, for alpha, you would require to define your thermal diffusivity, thermal conductivity, and your specific heat constant. So all those parameters have to be introduced. So this is where you will be introducing all of those in your transport properties. Okay, I'll show you side by side the original files in transport properties once we've done compiling this, as well as the files that are modified. So in your transport properties, this particular block is just reading your transport properties file, and then down. Now in your original scalar transport form, you have the diffusivity. Okay. Now here they are diffusing the temperature. So you have diffusivity with respect to temperature. That's why it's set to dt. But in our case, we want to specify the diffusivity on the scalar. So that's why we have a diffusivity for scalar 1, ds1, and we have the diffusivity for scalar 2, ds2. So these two we have defined. Along with that, we have Arrhenius equation. So the temperature block, we just copied it from top to down. And here we will be specifying the Arrhenius coefficients. So over here, as I mentioned, for the energy equation alpha, you have rho, you have Cp, you have kappa, that is your thermal diffusivity. Sorry, you have, this is your thermal conductivity kappa, and thermal diffusivity is your alpha. And along with this, we have defined a Ks block. Okay, so now this Ks is just your, as I said, the left-hand side in this equation, Ks, we want Ks to solve this equation. So we've defined a block named Ks. And within that, we have specified A, E, A, R, all of these parameters that were in Arrhenius equation. And these particular equations will be constant. That's why they will be set in your transport property under the constant directory. So they will remain constant throughout the equation. And anything addition to that, it will be solved using the whole simulation. Okay. So as I said, so you are specifying that Ks block. So this is where you would specify the Ks, and then you have the additional parameters, that is your create phi, create FE model, and condition. These are some basic header files that you require for OpenFOAM to understand and to simulate your whole simulation. So this is your header files, okay, both of these. Now, once you have introduced those header files, then go back to your C file. So the very beginning, you have the simple loop, okay? So while your simulation is running, everything within this, what you want to solve while your simulation is running will come within your while loop. Okay. Now in C, C++, you will know that you have to specify things and how does a while loop work. So I'm not going to explain how does a while loop and all those things work. But whenever you want to solve something within that equation time or the simulation time, you specify it within your while loop. So while your simple algorithm or your simple loop is running, you want to solve for the Ks equation. So by here we specified that Ks equation, Ks is equal to A, and then we have E raised to EA and this divided by RT. So once, okay, I'll explain the create fields again, a little bit slow this time. So the very beginning, you would have a scalar, okay? We want to introduce two scalars. So we have scalar 1 and we have scalar 2. So this is where you will specify your initial boundary conditions for scalar 1 and scalar 2. So that is why we're introducing it under wall scalar 1, scalar field. So these will be your boundary fields or your initial boundary conditions. So this is where you will specify that within these two blocks. And then you have your velocity and you have your temperature. So these two are already there in the original solver. So you can just copy those over into your modified files. Okay. Then once you're done with setting up your initial boundary condition files, you move on to the transport properties. Now in transport properties, in the original file, you have within transport properties, you just have the diffusivity and you would have some additional parameters. I can open and show it to you. It will better help understand. So this is your modified folder. So under transport properties. Okay. So this is your original transport property. So you would have dt and you would have nu. You would only specifying these two parameters. Okay, that is your diffusivity and your kinematic viscosity. But in your modified folder, you see in the modified folder, we have additional parameters. Now, if you were to just type in these parameters within your constant folder, OpenFOAM would just neglect it because these are not defined in your solver itself. So it will just try to bypass everything. So it would only see dt and it would see nu. But over here, we want to introduce the diffusivity for scalar 1, scalar 2. We want to introduce rho, Cp, kappa, and then we want to solve the RNA's coefficients as well. So all of these have to be introduced. So to introduce these, you would modify your header files as well as the .c files for those to be solved during your equation or during your simulation. So over here in your transport properties, we are mentioning that we want to solve first for ds1, that is the diffusivity of scalar 1, then for diffusivity of scalar 2, and then we want to solve for RNA's equation. So in RNA's equation, we specified the coefficients over here. What are the parameters that need to be solved and which are the constant parameters you need to type in your transport properties? Those are mentioned over here. Similarly, you have introduced that KS block. So if you see this, so over here, you have the KS block. Within these, you have type RNAs, and then you have the parameters of this. So these are specified in your header file. Okay, the original header file. This is your modified header file. Now, once you've done modifying your header files, you can go to the .c file. So within .c, as I was explaining, anything you want to solve during your simulation and all comes within this while loop. And if you mess up something over here, you will obviously get a prompt on the terminal itself saying that a particular line in this particular code is not proper. So you can rectify those. I'll show you how to get started with the modifying part of a solver as well. OpenFOAM has its own documentation, so it will be very beneficial for you. So the very first thing you want to solve is this KS equation. So we've mentioned all of these parameters in the header file. So it can fetch those headers. And so it'll know like what is A, what is EA, what is RT. So all those parameters are mentioned over there. Whereas in the original file, it is only solving the T equation. Okay. So this is the difference. In the original scalar transport, it is only solving for temperature. Whereas over here, we are solving for scalar 1 equation and scalar 2 equation. Now again, in scalar 1 and scalar 2, now I'll show you the equation back again. So this was our original equation. Okay, so if we just rearrange a few of these, like if you take the diffusion term and you bring it to the left hand side, you would have a minus sign in front of it, and where you have minus RC, that is your reaction term, you can replace that with Kc. Okay, so you can remember this equation. You have d by dt of C plus the velocity term, that is you can take as phi, and then you have your gradient and you have C. Okay. So the same thing is over here. So you have FVM. So we're using finite volume method. And over here, you would have d by dt of scalar 1. Okay. So this is your first term. Then you have phi and you have C. Okay. So over here, again, you have scalar 1. So you have plus FVM of divergence of phi, and then you have scalar 1. Okay. And then you have minus. As I said, if you rearrange this, you would have this diffusion term coming this side, so you would have a minus sign. So minus and this term. So you would have minus Laplacian ds1, that's your diffusion term, and then you would have scalar. And in the end, equal to Ks of scalar. So basically multiply by scalar. So this is your temperature dependent part. You're on the right hand side. Okay, now this will be solved using RNS equation. That's why we mentioned on top over here that Ks over here, this Ks will be found through this equation. So we've done this for one scalar 1 equation. Similarly, for scalar 2, you can just repeat the whole thing. You can change the name to scalar 2. Now, in case we were to have additional scalar, so you can again increase these blocks into multiple blocks. And then you have some relaxation parameters and all you can set. So those are set over here. So with this, you have specified and you have introduced the equation in your C file, that is in your modified solver. And you have also modified the header files. Anything that is dependent on those equations, you've mentioned those also over here. Okay. Now, once you've modified all of these, how do you compile it? So this is where you would go back to your case file that we have. So you would have the case file, you would go to solver and you would open it. So, okay. So once you're within this, basically you have the header file and you have the C file, you can right click, you can open in terminal. So you can just type WSL, enter the Ubuntu environment, and I'll type OF9. Most of you must have created an alias. So I'm using OpenFOAM 9. Now the very first thing you would do once you're within this folder is type wclean to clean anything that was previously made or any residual files that are remaining in this. You just clear the whole thing and then you can type wmake. So when you type wmake, it will start compiling your solver. It will start reading that .c file, it will read the header files. Anything, if anything is missing, it will just show it in bright red. It can show it to you. So say we have this equation, okay? Or we have this one. And now over here, we've defined Ks and we've told to solve this equation. So suppose I would to comment out this part and I would say wclean and wmake. Okay. So let's wait for a minute. Okay. So it did not throw an error, but if I were to solve this, it wouldn't know where to fetch any of these equations. Okay. Let's say over here, we delete something out. Some of the header files. We'll remove this header file. Let's save this. Let's try again. So see, if you miss out any of the header files or you don't define something, it will throw errors like this in bright red. It will show that error KS was not declared. Then MAC phi, it does not understand what are these parameters. That's why if you do not mention those in your header files, your C file won't understand where to fetch those things from. So we'll save this and we create again, we compile our solver. So if you don't get any errors, that means your solver is compiled properly. To test those out, you can always go to one of these folders. Like for now, I'll show you the testing part later. So before going to the folder itself, I'll show you where can you find out a documentation to modify a solver. Okay. So if you go to Google and you just type OpenFOAM Programmer's Guide, the very first option that you have, you can click that. So over here, you can download this PDF. Within this, they have mentioned what and where you can change things. If you are developing your own solver, how can you do that? If you have any equations that you want to set. Now I told you about the FVM and there are different methods, like finite volume method is there. So those you can find on page 35. Okay. So over here, if you're solving for a Laplacian term, and these are some of your this, so you can type Laplacian phi. So anything that you are like, we would write it in simple Greek letters. You can mention those in a coding language pattern. So how OpenFOAM is designed, it gives a whole document on that. And additionally, most of you might know this or might not know. If you scroll down a bit, scroll on top, there's one particular table that gives you the dimensioning of what and where exactly are the dimensions set to. Because most of us, when we copy out a tutorial, we don't really see the units that we are putting in. Okay. So over here, if you have that, like if you open any of the files and you see on top, you have a set of numbers over here. So if you have a velocity, you would have meter per square, something like that. So all those parameters here, it mentions that first one in this whole section is mass, second one is length, time, temperature, quantity, all those things. So you can go through this document. It's a very detailed document. It is really good if you're trying to develop something on your own. So it specifies everything, how to incorporate an equation within OpenFOAM environment, what particular header files you would require, how to find those, all those things are mentioned within this document. So you can have a read of this. Okay. But coming back to the case that we have, so this was a case. We have compiled our solver under solver setup. And now you would have two additional folders. Okay. One is for plug flow, other one is for laminar flow. So I'll show you the domain that we have. So this is our domain. It's just a 3D pipe. We have an inlet, we have an outlet, and these are the walls. Now in this, we are going to be introducing the scalar at the inlet. Okay. We are keeping scalar 1 as 1. That is means we're giving scalar 1 and scalar 2, we are keeping it as a product. We want to see how the scalar 2 develop. So we are giving the whole inlet as scalar 1. But before we do that, we have to first initialize the flow. So we will first solve simple form, but just to get the flow parameter out. Then we would solve the energy equation using scalar transport form, that we will get the temperature equations and all of those. And then we will copy those outputs into the input of your scalar transport form, the modified one. Okay, so I will explain that. So first we have the laminar flow. Okay, you can open this, you can open either of these. So you can open steady, and then you have the flow and you have the steady scalar. So if you open this particular file, you can go to the control dict. This is where you can see the solver that has been used. So you can close this part. You don't really need this now. So as I was saying, that in the flow case, you would first have to solve the simple algorithm to generate out the velocity. Then we would have to solve scalar transport form to generate out the temperature values. And then we will take these two values, that is the output of this particular case, and feed it in as an input. Okay. I know it's a bit complex. For at least a beginner, it is too complex, but once you start learning OpenFOAM more, you will realize that most of the solvers, whenever you're solving for additional parameters like these, you have to initialize your flow first, and then you can go ahead and remove some of the additional parameters that you require to solve. So these are pretty much common once you start understanding OpenFOAM and CFD as a whole. So in our case, we will be solving first the flow equations, and then the temperature equations, and feeding that to solve the scalar equation. So first, can show you. So if you notice, those were the simple and the scalar transport form, and this was for the flow. And if you open the steady state scalar, and you again open control dict. So over here you have our modified solver. Okay. So this is where you will be solving all the equations that we've put in there. So going back to the flow case. So first we will solve for the flow, and then we will move on to the scalar part. So again, within this flow file, you can have a README file. This README file will mention how to run this case. Okay, so first it says to open the directory, run cd command, block mission, all those stuff. So what we do is, so first we will just run the all run flow up. The README file says you should first run the all run flow up, that is your velocity and pressure. And then you have to make the change in your control dict. So from here, you have to change simple form. You can just comment it out and then you can enable scalar transport flow. Okay, you can do this, or for those of you who are already comfortable with OpenFOAM, you can try modifying this case as well. So again, there is a lot of scope in modifying these cases. You can create your own custom solver which will solve for velocity and temperature together. So you can make your own solver within this as well. So again, you can take it up as a added thing. If you want to try, you can try. So for this particular demonstration, first we will run the all run flow UP. So we will open this. We'll see the commands that you have to run. Okay, you can ignore the very first command. So you have block mesh that will create your mesh. For those of you who are new, you have a set of commands in OpenFOAM that when you type it in your terminal, it will execute a specific thing. Like you have block mesh, it will create your mesh. Then you have decompose, it will decompose your domain into a smaller section, you can say. Like if you have, say my screen is this big, it will decompose it 8 times. Like it will separate, or it will break this screen into 8 particular pieces, and it will solve each of those pieces on a particular processor that you have. So now if your processor has 8 cores, you can break it down into 8, and each of those cores will solve a particular section of your domain. So that is what your decompose does. NPI run is just enabling your parallelization. So if you're going to run this in parallel, now on my system, I have 6 cores. So I can drop it down to 4 because I don't want to load all 6. So I will change this to 4. And if you have 8 cores, you can run. So there's a handy way to check how many cores you have on your system. You can type ls CPU, and you can then just scroll on top. So over here under cores per socket, you will have it mentioned. So in my case, I have 6. So I will keep it at around 4. Can decompose my domain in 4. Can close this terminal. So I've changed this to 4, but only changing in your all run folder is not going to do much. So you have to go to your system, and within system, you would have a decompose pardict. For those of you who already know this, it is really irrelevant. We'll know how to change that. But for people who are new, it's a handy thing to keep in mind. Otherwise, you might face some error when you try to directly run the whole case. So you can change this number of subdomains to 4, because I think most of the people will have 4 cores at least. So once you're done with this, again, you can right click, open in terminal, and type WSL OF9. So I can either manually type each of those commands, like I can type block mesh, or I can run the all run file. Do bash all run UP. Okay. So first it will start executing my block mesh. So you can see it's creating the mesh first. This will take a few seconds because the mesh is not really that robust. So once it has created your mesh, it will start to decompose. So I have specified mine to 4. So it will decompose it into 4 domains, 4 subdomains. And then it will start your simulation. Now the simulation is set to 50. So now it's starting at time 1. It will take some time now. Okay. So I already have this case that is already run. So once you are done, stop this. It takes some time. Okay. So you can press Control C to stop the whole equation, whole simulation. So once you're done solving for you will get some, see over here, I have this run case flow. So I've solved already. So it will give you one file that is 50. So you can copy the U folder from this into your 0 folder. Okay. So you will copy this. So you open 50, you copy the U file from here and you place it in your 0 folder. So once you've done this, go back to this case. So once you've done that, you go to System, Control Dict, and you change this particular application from simple form to scalar transport form. You do this, save this, can you go back, and then you can do an all clean, because the all clean won't really remove the 0 folder. So bash all clean. Okay. Refresh it. So again, now once you've done that, your 50 folder is gone, but that U folder, what you have copied from that 50 will remain inside this. Okay, so see, now this is the original that I have. Okay, so this was your original U file, but once you copy the run case file, it's coming in the middle. So this is the run case that I have. So if you were to open this U file, so you would see once you run that simulation, it will store some data. So we need this data for the temperature. And then once the temperature is also solved, we need this run data for the scalar. Okay. So this is what I mean by when you're copying a U folder into your zero folder. Okay. So once you've changed in your system, controlled it, you've changed the application, scalar transport form, you can then run the all run float T. Okay, so we'll open this folder. So you see again, it is block mesh, decompose par. Let's change this to 4. And here it is solving scalar transport form. This will solve your energy equation. So once you're done solving that, you will again get that 50 folder. Like over here, you will get this 50. I've completed it for U and for T. So once you've got this 50 folder, you can copy this entire folder into your scalar steady state. Okay. Now in your scalar, I have renamed this folder to 0.org. You can also do the same. So okay. Because we require scalar 1 and scalar 2. Additionally, we require the previous run case. Okay. Like what we've run for the flow, we only require T and U from those. So you can keep those as 0.org. So you can view those files. And additionally, you can then paste all the remaining ones. So over here, I have pasted these files in the run case for U and then for T as well. Okay, so this is for T. So it has already solved these equations. And now we're just introducing the scalar and we want to see how did that scalar move. So you can see the scalar 1, we have just mentioned it as 1, that is that inlet. So at the inlet, it is completely coming. So we have that. Whereas for scalar 2, we have set it to 0 because scalar 2 would be a product. Your first one is going to react and then we want to see what happens to the product itself. So again, if you have multiple scalars, you can check. We have a lab migration dedicated to how this particular scalar thing works. So you can check that out as well. So on our site, we have a lab migration. If you scroll down on the left to lab migration, we have this lab migration. You can go to completed labs and the very first one, stimulation lab. Within this, we have the exact same thing, but without the RNS equation. So we have solved same thing. You're checking scalar 1, and over here we've introduced, say, scalar 1 in the top half of the cylinder. Then we have scalar 2 generating at the bottom half. So all those combinations are there. So you can check that out also if you want to understand more about the scalar part. Now, in this particular demonstration, we are just showing you how to modify the solver. We're not really diving deep into the scalar part. So once you have done that, once you've copied your 0 folder and modified everything over here, you can go to the. So this is how it will look for you. You would have this basic 0. So I changed the 0 to 0.org and made a copy of it as well and named it 0. And I pasted all my TU files inside this. So once you're done with this, you can again use the all run file. This all run, it is again block mesh decompose. Then you divide your whole domain into 8 parts. Here in my case, we'll divide into 4. And here is where you will run your new scalar form modified in parallel. And then you reconstruct the data. So let's go back to the run case. So this is the run one. So you can open it. WSL, OF9. And you can open this in paraform built-in. The reason why using built-in is because in the regular paraform version, for some reason it does not show your so this is your pipe. You have the pipe geometry. And so over here you can see the temperature, velocity, Ks that it is solved, scalar 1 and scalar 2. So all these parameters you can view. Now you can read the report. In that they have changed a few things. They have mentioned what they're trying to find, what results. Now this one, I only showed you about the modification, but in that one, they were trying to find out the residence time in the pipe itself. So all those parameters they're trying to find out. Let's take a slice of this. There's slice. Let's say scalar 1. So on the left-hand side, we are giving a scalar. And then as time passes, you have the scalar moving from left to right without disturbing the flow. That is why we've initialized the flow first, and then we are introducing that scalar within that initialized flow itself. So this is the whole setup for this case. Now in the lab migration that we have, in that we had introduced two scalars. Okay. So one is on the top half and the bottom half is a product. So when this top one is forming, and we've introduced diffusion in that as well. So if you increase the diffusivity term, so in this, you go down to constant and you open transport properties. Okay. So over here, we've set diffusion to 0 for scalar 1 and scalar 2. So you can play around with all of these factors. Now, most of the parameters are set for water. So all these remaining constant parameters will be for water, whereas your diffusivity, you can change based on how you want to simulate or what you want to find. So if you want to just check what happens when you increase scalar 1 diffusivity or scalar 2 diffusivity, you can increase that. You can put it as some factor over here, you can increase the diffusivity of your thermal diffusivity as well. You can change all of these parameters. You can see how it affects your whole simulation. So all of these are possible just because you have modified your solver. If you were to just simply add these names and these dimensions into your folder, you won't really get anything. And it might even give you an error if you put that solver name because it has not compiled anything. So in order to compile a solver, you need to first modify the header files. You need to introduce the equation you're trying to find, and then you can compile that and you can run it in your simulation. Now, in our case, the simulation itself was quite complex, but in your case, you might just want to incorporate temperature in a simple algorithm. You can do that as well. There are many people who have done that. You have solvers for that as well, but if you want to try something out, you can do that. You can always introduce temperature within the simple algorithm. Or if you have some multi-phase case and you want to introduce another thermophysical property or another property that you have, you can always modify that as well, add in those equations, and you can do those things. So there is no limit when it comes to modifying anything in OpenFOAM. It's as Mr. Advait said, it's an open source software. You can play around with it. If you have something specific to your case, you can always model that entire solver from scratch, or you can take help of pre-existing solvers and you can just modify those up to a level that is satisfiable to you. So there is no restrictions when it comes to OpenFOAM. That is why we try to tell people to learn OpenFOAM, because these restrictions are not there. Like if you were to do the same thing in ANSYS or in any of the other commercial solvers, you would have to write your own code or try to post-process something in that end. But here you can do that in the front end, in your back end itself, and you can do it in your simulation stage itself. You don't have to really post-process the additional data, or you have to put some additional parameter and then try to find out something. Okay. So this was it about the whole solver modification part. Now, if you have any questions, I'll be happy to answer that. If it is too complex, we can always take it up at the 5 o'clock Q&A session that we have. Can't we use the same mesh while solving for T after U? T after U, you are using the same mesh. Okay. So in the flow simulation, you're only changing the solver, whereas your mesh remains constant. Okay. I think that is the question by Mr. Abhishek.
Excuse me, sir.
Yes, Himant.
How can we change the element size
The
if
element
we
size.
required? If we require.
Element size as in the mesh element size.
Sir.
Okay. So show that. Usually this we always take it up in the basic workshops that we have. This time we are just focusing on demonstrating most of the things. I'll just show you. It's not a big deal. So
Okay.
you can go to system and you have your block mesh dipped. Okay. So
Okay.
these are your vertices. These are your blocks. So if you want to change any of the element size that you want, you can do it within these three numbers. Okay. So
Okay.
this is your X, Y, and Z direction. So depending on how you want to change the cell size, you can change it within this. Just remember that the pipe is at least the lengthwise, it is made in your YZ plane. Okay.
Okay. Okay, sir. Thank you.
Yeah. Okay. What is plug flow case? Okay. So depending on the flow itself, there are different types. Now in a plug flow, it's something like a normal thing. So if you see the more detailed example of what is a plug flow and all of those are in the lab migration. That is why I directed you towards that. You can read the report that has been made over here, because this explains there are in total 10 experiments. In each of those, they are trying to explain each of these parameters that you have questions on. So you can read all of these solutions. They have the simulation case files as well. So if you want to start off with scalar and you're interested in learning about scalar transport and chemical equations as a whole, you can read this whole lab migration. It's really good. Is it possible to GNU plot in running condition? What exactly do you mean by GNU plot?
I guess they are asking about the residuals.
Yeah. The residuals are you can plot it. You can directly just form monitor and all this. Mr. Aditya, we had our installation sessions yesterday and on Friday. If you're still facing any installation errors, you can always email us on the email ID provided in the email. We will try to solve those issues over there. This is to work in the same Ubuntu directory as we can copy case in any directory. You can copy it into any directory. Like if you want, you can copy it into your downloads or your document as well. But remember that your username, like in my case, my username has a space, at least for Windows, because I have to add my name and last name. So that causes an error with Ubuntu because you cannot have any spaces in your directory. That's why it is always advisable to copy everything into a run directory, because that segregates out which versions also you're using. Like for OpenFOAM 2412, you have one particular directory. Show you. So if I were to open home, and over here I have OpenFOAM. So you see over here I have multiple versions. So if you're running something specifically on OpenFOAM 9, you will have those files saved in 9. If you have something in 24, you should be saved in 24. So you won't have to then think where exactly and which version are you using for this particular file. Which lab migration? Okay. So for lab migration, you can go to completed lab migration, go to completed labs, and the very first one, stimulation lab. This is by Professor Dheeraj Garg of Shiv Nadar University. You can click that, and then you can view the solution. You can view solutions over here. The current case study is just an extension work of these particular labs. So that's why it is not that detailed when it comes to the flow part. It is just purely focused more on the simulation part for the solver itself, like solver development part. How to create the new solid surface. What do you mean by new solid surface? Could you elaborate a bit, Narendra? For VirtualBox, yes, you can use, like if you're using VirtualBox and it is an Ubuntu environment, you can really open the file in any folder that you have. Because for Ubuntu, it's not really specific. It's only for Windows that we tell people to save everything in your run directory, because you are using a subsystem, right, for Linux. That is why we tell you to save everything over there. And Narendra, if you're asking for solid surface, create the new solid surface. Both, if you're trying to make any of the solid surface, you would have to create a mesh that you would do in your block mesh itself. So I'm not really understanding your question.
So, sir, if you don't mind, is there any limits to mesh?
Sorry?
And, is there any limits to mesh?
The only limit when it comes to meshing is your RAM. So if you have like a 16 GB RAM, a cell size of say one lakh, like 10 lakhs to 1 crore should be fine. Above that, it will directly just crash.
It will be run or not?
It will run, but it will be very slow, and most probably it might crash also.
Okay.
So for 16 GB, there's a limitation. If you're on 32 GB or 64, it is still bearable. But for
Okay.
16 on a laptop, you'll face some issues when it comes to meshing at that fine level.
Okay. Okay, sir. Thank you, sir.
In any case, how do we decide which solver uses a particular case? Because a lot of solvers. Okay. So when you're trying to modify a solver, there are some parameters and some equations that you will require, right? Now, in our case, we wanted to introduce a scalar, and we also wanted to solve for energy and the Navier-Stokes equation, that is your flow equations. So flow equations are pretty simple. You have the simple form algorithm and the simple form solver. Then for any of the energy equations, you will have scalar transport, or you will have like any of the basic solvers. Those are solving energy equations. That's why I showed you the path, right? You can go to the solver section and you can open all of these solvers. If you have the time, you can always open all of these solvers and check what equations are they solving. You can also find the same thing easier if you open your tutorial, because your tutorial is based on different types of simulation. So suppose if I want to try for heat transfer with buoyancy, okay? So with buoyancy, you have buoyant simple form. But say you want to introduce something additional. So you know that buoyant simple form is solving your buoyancy forces also, and it is solving your flow parameters as well, along with the energy equation and all of those stuff. And you want to modify something, so you can use this solver. Like you can go back to tutorials or to OpenFOAM, go to applications, to solver, and you can go back to heat transfer and you can open the buoyant simple form. And then you can try modifying those. Yeah, as Manzil said, the tutorials are categorized based on solvers. So you can open the tutorials and see which solver is it using.
Hello.
Yes, Arijit.
I just have one question. That is, say for example, if I have one file that is there in the tutorial, is it means possible that is also there in the application?
Yeah. See, your tutorials are segregated based on the solver itself.
Okay.
They are both interconnected because they are going to be solving some particular equations. So for that very equation, you have a particular solver already in place. So
Okay,
they both
means
are linked.
tutorial and application both have the same kind of list.
Yes.
Okay. Thank you.
Thanks. Bye bye.